Yes. Can I begin? Okay. So before I continue, just I want to return for a minute to what I discussed in the last part of my talk yesterday. I mentioned a polar factorization theorem by Brenier, and I forgot to mention some conditions. So actually, the condition for polar factorization is that both measures mu and nu will be absolutely continuous with respect to the bed. And in addition, they have to be belong to the to P2 to P2 of RD. So they have a finite second moment in RD. And the reason for this demand is that to prove this factorization, we have to take the inverse of the mapping that the gradient mapping that push mu to nu. And in general, every convex function is differentiable almost everywhere with respect to the bed. So of course we need the absolute continuity of mu with respect to the bed to ensure that we have this mapping is defined mu almost everywhere. But in order to have an inverse mapping that push mu to nu, we have to take the Legendre transform of phi, the gradient of the Legendre transform of phi is the inverse of the gradient of phi or a convex function. But again, this is defined only on a set which is almost everywhere with respect to the bed. So we need also mu to be absolutely continuous with respect to the bed. Then when we have this condition, we can prove by just inverting that HT, which push mu to ni, it can be represented uniquely as the gradient of phi times, times S, where S is a mapping which preserves the mu measure. So just, yeah, when we calculate it, we have to invert phi. So this is the condition. So okay, so let us continue from here. And now this is the time we can define this object, which is called Wasserstein metric. So we define it like as the Kantorovich distance with respect to the cost x minus y to the power p. And we take the p root of this, and of course it is defined for measures in the space p. P is the moment of probability measures. P is bigger or equal to 1. Why is it a metric? We will prove that it is really satisfied triangle inequality, and the proof follows by this by using this integration theorem. So what does this integration theorem tell us? For any positive measure of mu on a space y, and some measurable map pushing y to subspace z, we can find a family of probability measure q for each z, for each point z in y. That's a probability measure in py. We can call it a conditional probability of q when given z, such that the measure q is given as the integral. Can be disintegrated in this form as an integral of this conditional probability times this push forward of the measure q by this function pi. So we take three measures, which is mu, sigma, nu, and we choose, we take the gamma plus to be the optimal transport from mu to sigma. This will be the optimal one. And we take, so this will have a marginals mu and sigma, and we take gamma minus to be the optimal one which push sigma to nu. And we disintegrate each of them. So, with respect to pi, which is projection on the second component, x and y, we take sigma will be, by this definition, the projection of gamma plus with respect to this pi, and this integration will be just this one, right? According to this rule. So this will be the integral with respect to the measure sigma over q plus. And it's the same thing for gamma minus. With this projection which maps on the first component, so we have this integration of gamma minus. Now we compose, we construct this measure on a triple space, x, y, and z, by just taking the sigma measure and multiply it by these two conditional probability measure, q plus y and q minus y. So by this construction, you see that if you project on in the three space on the first two components, we just get gamma plus. On the last two components, 2, 3, we get gamma minus. And if we project on the first and third component, we get something which we call gamma 0, and this lives in the space pi mu nu. So this gamma 0 is an admissible transport, but not necessarily optimal, of course, which push mu to nu. Now we make the following chain of inequalities. So the Wasserstein distance between mu to nu, this is smaller or equal than the LP norm of x minus z with respect to gamma 0, because we said gamma 0 is not necessarily optimal. So we have this inequality. But now we can consider this as an integral over the 3 space with respect to the measure gamma, because this is an integration on x, y, and z, but this function does not depend on y, so the integral of y just disappear and leave us with this integral over the space x, y, and z. And then we use the regular inequality, triangle inequality for LP norm. So this is x minus z, we plug it to the x minus y plus y minus z on the triple space. And then we, again, because x minus y does not depend on z, we integrate over z, we get x minus y with the LP norm of gamma plus, and y minus z with the LP norm of gamma minus, which are exactly the Wasserstein distance, because we assume that gamma plus and gamma minus are optimal. So we have this inequality, triangle inequality, and we prove that this is indeed a metric on set of probability measures. Okay? So let's go and see what we can say more about it. So if, well, in fact, if you look at the compact spaces, we can easily see that for any p bigger equal to 1, this metric is a metrization of a weak star topology. First, we have this inequality that's just Holder. The first inequality is just Holder, right? We integrate x minus y to the power 1, and estimated by Holder inequality to x minus y to the power p and times 1 to the power whatever. And this one, this inequality, because we assume the set omega is compact, so this is going to be something like the diameter of this, so x minus y to the p is smaller than some constant time x minus y, if the domain has this finite diameter. So it's enough to show it for W1. W1 is a metrization of the weak star topology. W1 has a very special dual representation. Remember that the dual representation of W any cost function, in particular W Wasserstein, is that the supremum of the integral well, phi x plus psi y is equal to I want to equal 1 x minus y. But then when we look at this, we can replace psi by its C transform with this C. So we already saw that P Cx is just that all the C concave function with this C are Lifshitz 1 function, and the C concave of a Lifshitz 1 function is just minus this function. So in this case, we have just the supremum of the integral of phi x times d mu minus d nu. And the supremum is all function phi in lip 1, all function which has constant Lipschitz 1. So this is a very elegant representation of the very useful representation of the Wasserstein-1 matrix. So since the space of Lifshitz function are dense in the set of continuous functions on a compact set, we immediately see that convergence in W1 leads to weak convergence, because if the supernorm converge, so if mu n converge in W1 to mu, then the supernorm converge, then evidently the integral of phi d mu n minus d mu is going to 0 for any phi, for any Lipschitz phi, for any function Lipschitz phi, therefore for any function phi in C0. Okay, so this is one direction. In the other direction, suppose we have a weak convergence. So if you look at all the set of Lipschitz-1 function, and let's fix some point and consider the set of all function in Lipschitz-1, which are 0 at some point. We can always reduce a constant for the function for the function phi, for the function oculative, for its phi. And if you take for this, you can add or subtract constant for phi without changing this integral, of course, because these are two probability measures. So, so this sort of function is compact in the set C0, and the sort of compacted bounded in C0, and the functional. If you look at for any mu, the functional f of mu equal the integral of phi d mu, this all these functionals are equicontinuous on the space of C0 because f mu, excuse me, f mu phi, f mu phi. That's the functional of phi determined by mu. These are equicontinuous because f phi 1 minus f phi 2 smaller or equal than phi 1 minus phi 2 in the infinity norm, right? Because this is a probability measure. So we know that if we have equicontinuous set on a compact on a compact set, and if they converge weakly, it means that they converge portwise. But if they converge pointwise, they also converge uniformly. That's, we know, for equicontinuous family on a compact space. So to converge uniformly precisely implies convergence of the supremum. So it implies convergence in W1. Okay? So this is a reason why we claim that we have a factorization of the weak star topology by any of the Wasserstein spaces. This is on compact space. If you go to Rn, for example, then we have to add something. Because the convergence in dual C0 may not converge to probability measure, mass may run to infinity. So we need another condition. So the condition is that you have a convergence of mu n to mu in Wasserstein P, if and only if they are converged weak star, and also the P moment mu n converge to the P moment of mu. So this takes care of a mass running to infinity. And one condition is very easy to see. We use the density of the Lewis function in C0 to show that mu n converge weakly to mu, and the triangle inequality to show that mu n converge, the distance between mu n to delta 0 converge to mu to delta 0, because the triangle inequality tells us that we take the difference between these two will be smaller than the distance between mu n to mu, because we already noted WP is a metric. Okay, so we get to this point, and now I should have to do another headline, but I want to talk about curves in WP space. So that's our orbits of probability measure from time like variable t to a probability to the C, and define what does it mean that this curve is absolutely continuous with respect to WP. So it means that by the way, I forgot to mention some remark that so this Wasserstein distance, of course, is between measures is much weaker than the convergence in absolute, in total variation. We know that we can define a total variation metric between probability measure. This is just the extension of the L1 distance between the densities, but it's not equivalent, of course, to weak convergence. But we can represent also the total variation norm as a Wasserstein distance with respect to the discrete metric. Is not Wasserstein, but call it Kantorovich. Kantorovich distance with respect to the discrete metric, which is the distance between x and y is equal either 0 if x not equal y, and 1 if x equal y. So this is a nice observation that you can consider. This, of course, distance is not equivalent to the metric, therefore they are not equivalent, but it's nice to see that this is really come into this context. Let me return now to this statement. When we look at the orbit of probability measures depending on t, we can define something like a derivative. So, if this has a property of absolute continuous, what is absolute continuous? Means that in WP, it means that the distance WP between mu t and mu tau is controlled by the integral of some function g, which is in L1, function of t, which is in L1. Okay, this means that this is absolutely continuous, and if g is a constant, then it's a Lifshitz. And by Rademacher theorem, there exists always a derivative in this sense. So we defined the metric derivative of mu as this limit, which exists for almost any t, right? well, you can also reparameterize it in time to have a curve with a Lipschitz 1 curve. So this justifies the Rademacher theorem, the application of Rademacher theorem to conclude that we have this metric differentiability almost everywhere. Okay, so let me give you some intuition a little bit. What does it mean that we have such a family of measures that changing in time, probability measures changing in time? If we follow this family of measures evolving in time, let's say this idea of the density. So at one time it looks like this, other time it looks like this. And we want to say, well, there is some velocity field acting here, which make this bunch of particles move according to what we see. So suppose, what is this velocity field can be? How can we determine it? Suppose that the density is constant all the time. Maybe something is moving, but we don't see it because the density is all the time constant. So we'll say, well, if we don't know anything else, velocity is 0. But suppose it's not precisely constant, there is some small ripple here. And this small ripple moves with velocity v. Right? What will be the velocity of this distribution? Will it be v? Well, if this is very small ripple, and we take this ripple to be to smaller and smaller, we'll get, and if we think that should be some continuity here, so this will be, it cannot be v, right? Because in the limit of flat profile, we see 0, right? So the point is that we want to look at, we want to consider this in the form of continuity equation. So this is a continuity equation for measure, and we understand it in the weak form, in the form of distribution. In duality with C0. So here is a theorem, quite deep theorem. I will not prove it, but it's important to know it. So if mu t is absolutely continuous, then there always exists a vector field in this space, which is L1 in t and into LP of mu t for each t. And this, we satisfy this continuity equation in the sense of distribution, means that we multiply it by test function, and this divergence of become the v times grad of test function times u, and also minus mu times the t derivative of v. So, and whatever, and moreover, then the norm of v, for almost any t, the norm of v will be the metric derivative of mu. And the converse also, if we know that there is a vector field mu t, a vt, which satisfies this continuity equation in this space, then mu t is absolutely continuous in Wasserstein P, and we have this inequality. So in general, of course, the velocity field doesn't have to be unique. Look for the even smooth distribution. If we have a continuity equation in the classical sense. So at least if rho is positive everywhere, we can add to V some vector field of a rho, which is free divergence. And it's the same equation, right? If you add to V this term, will satisfy the equation. So we cannot expect uniqueness for the velocity field which drive this density. Well, at least if rho is the density is positive everywhere. If it's not positive everywhere, you may have uniqueness. But this is not guaranteed in general. Another remark that you could see here is in general, we cannot say that there's a particle flow because this V doesn't have to be to support a flow. We cannot have a solution. We don't necessarily have a solution for this ODE, x dot equal V xt. So we cannot construct particle paths unless V is the Lifshitz. If this is really Lifshitz or locally Lifshitz, at least we can have a uniqueness for the solution, but nobody guaranteed that V, the theorem does not guarantee any Lifshitzity on V. But if you look on geodesic path, or in the one-dimensional case, this is always support velocity field. And so let me tell you something about maybe. Let me tell you something about geodesic, then we turn back. So what is geodesic in metric spaces? So we have, in general, in metric space, we know that we can define the length of a path. And if this is a path space, then the distance between 2 points is just the infimum of the length of the orbit between them. So, for example, if this is a length space and alpha is between 0 and 1, then d to the alpha is still a metric, but not a length space. Space is geodesic if the infimum is always obtained. And for any geodesic, we can reparameterize the time such that the derivative of this orbit will be just from the interval 0 to 1, 0, 1 is just the distance between W0 to W1. So if we, so this is the general characterization of a geodesic, of a constant speed geodesics. A constant speed geodesics minimize the distance to power p for any p bigger than 1. This is among all absolutely continuous curve connecting W0 to W1. And another characterization is the distance between 2 points along the orbit is just absolute distance, p minus s absolute value times the distance between W0 to W1. This is true for any p and s is 0, 1. So this is a general statement about a curve in metric spaces. So here we return to Wasserstein distance, to the probability measure of Wasserstein distance. So if we have a convex domain in RD, and the mu net probability measure for p bigger than or equal to 1. And if gamma is an optimal plane connecting mu to nu, we can define this flow going from x times 0 to y at I1 by a linear segment. And then we can define a family of measure mu t by pushing this gamma, is a measure on xy, pushing this gamma to the point to the space x by this pi, right? Because this is a mapping from xy to the point in the section in the space x. So mu t is defined in this way, and in this way, this is a constant speed geodesics. So in particular, we prove this theorem implied that WP is a geodesic space. The proof for this statement, so in fact, it's enough to show that we have this inequality for each, we define mu t in this way, and we have to show that we have this inequality, the distance, WP distance between mu t and mu s is not bigger than s minus t times W, the distance between mu and nu. Why is that? Because, again, triangle inequality, the distance between mu and nu is smaller than the distance between mu and mu t, plus the distance between mu t to mu s, plus mu s to nu. And then if we have this inequality, we can estimate it from below by WP between mu and nu times t plus s by t plus s minus t plus 1 minus s, right? Because this one will be these distances. So this is just WP, and so we have equality all the way. So so we just have to prove this inequality. So again, we take we define the transport program between mu t to mu s in this way by taking this pi in two different times, t and s, and push gamma with this mapping. So we get some measure in the marginals mu t and mu s, and then the Wasserstein distance between mu t to mu s is certainly smaller than this because we don't know yet that gamma s t is optimal. But by definition of gamma st, this is just we can replace gamma st by the integral with respect to gamma and put gamma and put pi on the variable x and y. We get pi t and pi s acting on x and y. So this is just pi t of x minus pi s of pi t of xy minus pi s of xy, just s minus t times x minus y as absolute value, right? So if we take the p power and the p root, we get s minus t times this integral, right? And this is just the Wasserstein distance between mu and nu. So we have this inequality. We have this inequality, and so we proved that this is indeed geodesic. And the intuitive meaning is we just follow right line with velocity, which is proportional to the distance that we travel between x and y, right? This is t goes between 0 and 1, so the velocity here is just the proportional to the distance. Let me go back a little bit and tell you see some examples. So suppose mu t is given by some density, smooth density, positive. positive by bounded from below by some delta. So this will allow us to solve it, to find the velocity field in a classical way. So if we consider mu t as an orbit in W, I guess I want to write it WP. So we know that we have to minimize this functional under the constraint. So remember that the theorem says that in order to find the optimal velocity field, we have to minimize overall this norm. So we want to, so we have this continuity equation, and we put this, so the continuity equation is the rho dt phi minus the rho dt phi plus v dot grand phi times rho, and so phi is here a Lagrange multiplier for this functional. Put phi as a Lagrange multiplier, and then when we solve, when we minimize over v for each time, we get that v is just the gradient of this Lagrange multiplier to the power q minus 2, where q is the dual of p. And we substitute it. We get that we have to maximize. We have to maximize this in the space of function phi. So the maximum of this is solution of the Q Laplacian. So it turned out that the metric derivative of mu is just the gradient of this phi in the LQ norm with respect to mu at time t. Okay, and if p equal 2, this is just a solution of this linear elliptic equation for phi, taking into account that rho is strictly positive. And if omega is a bounded domain, then the natural boundary condition will be Neumann condition for phi. So we can always solve it and obtain the metric derivative of this orbit. What happens if we take something not regular, something like a combination of orbit along delta functions? So let's assume xi are orbit in space, and delta is our Dirac measures, and mi are constant positive numbers. Xi dot is in LP, so you can easily see that the mu derivative is just the mi times xi dot, and the Vt is any vector field which I assume the value xi dot on the point xi, because v is only defined on the support of the measure, and so we don't define it anywhere outside the support of the measure, which is just the point xi. So this is an important thing to observe, that if we assume mi are not constant, just a function, maybe even a small function of time, then mu is not absolutely continuous. But even if mu I are infinitely smooth, or even if we compose rho into two parts, rho 1 and rho 2, which has separate support, disjoint support, and the integral of each rho I in support is not constant in time, then this smooth density does not have a metric derivative, and in p bigger than 1, or any p bigger than 1. And the intuitive reason is because when you see something like this, you understand that something is going in infinite speed between one point to another, or one cluster to another, And so we don't have velocity field which is bounded in this norm, but we can have it in P equal 1. P equal 1 is the limit case where this such orbits can have a derivative, because P equal 1 actually allows infinite speed in the limit. Another way that you can think about, if you look at our orbits which are constant, so consider two particles, which was M1 and M2 moving along orbit X1, X2, and X1, and they have constant mass, and they meet somewhere, and then after they meet, they continue. So after they meet, they may have different masses. They don't have to keep the original masses. So why is that? Because when they meet, they can exchange mass. So such an orbit, even if they intersect, can have a jump in the masses, provided, of course, M1 star plus M2 star equal M1 plus M2. The mass is preserved because you cannot gain mass from any other place. So this is an example when you can expect metric derivative. And in fact, about 15 years ago, I considered this case, and I tried to look for a model where you have a family of particles which behaves in this way, and add to the Lagrangian also an energy which depends on the masses, such that energy which is sublinear in the masses. So if you add to the kinetic energy of this particle the mass h, so this we have. So let's look at kinetic mi xi dot square plus some energy which is somehow embedded in the mass, and you assume that h is such that sublinear in the masses, you get something which tend to merge. Well, because if you want to minimize the energy, you prefer to merge particles, and so this is a model for. At this time, I looked at this as a model of coagulation between particles. But later I realized that it's actually a model for branching process. And I hope to be able to talk about branching process later in this course. Okay. So we already have this. And this, the corollary which I also mentioned, that I write it here explicitly, that we can characterize the Wasserstein distance between two measures by a dynamical way, by taking the infimum of this energy. So we look for all paths of measure connecting nu0 to nu1, which satisfy the continuity equation with respect to this v. And so we minimize overall both v and mu. And if you write it in a different way, you get a convex function. Not in this way, but instead of using the variable mu and v, you use other variables. That was done by Brazis and Benamo, and they use it to construct a numerical method for calculation of the Wasserstein distance. Another corollary is that if there is a Monge solution, if a mapping, Monge mapping, which optimal transport mu0 to mu1, then mu_t can be written in this way. Right? This is also a deterministic orbit, which goes from the point x to the point 1 minus tx plus tx along the orbit. Okay, so this finish this part, and now I will move forward to the next object, which is optimal transport on one-dimensional domain. One-dimensional domain has a very specific form, and we can do some explicit calculation because actually we have just one relevant map between two measures. So the infimum is just actually on one measure. So what do we have in this case? If we are an ordered interval, then we can define the accumulation function. Actually, I remember 2 days ago I mentioned it when I claimed that we can find a matching between any two probability measures on the line. So I remind it again. So we take the accumulation function. This is the measure of this interval, semi-closed interval between x to minus infinity, and it's a monotone in the right continuous function. What does it function do? Well, if you think about it, this is just push the measure mu to the Lebesgue measure on the unit interval. A unit interval because mu has mass 1, right? So f of mu is taking value between 0 and 1. And the derivative of f u is just the canonical derivative of mu in respect to the Lebesgue measure. So we can define a pseudo inverse if because f is not always strictly monotone. But in any case, we can define its inverse this way. So we take the infimum of all t such that f mu t bigger or equal to x. It's really an inverse if f is strictly monotone, or monotone, just monotone actually. And it pushes the Lebesgue measure back into mu. So we see that if we could compose f of mu over x of the inverse with respect to other measure nu, we get a mapping which push mu to nu. And this map is a monotone. So it's if x1 is smaller than x2, then y1 will be smaller than y2. The image y1 will be smaller than y2. I will later return to this and explain what I want to say here. But so let's define what do we really mean by monotone plane. So plane or probability space on R times R is called monotone if for any 2 points in the support of this pi, the inequality of the first 2 components, x1 and x2, if x1 less than x2, then also y1 is less than y2, or sorry, less equal. You can characterize it with a label that I will not prove, but it's quite straightforward that if the monotone mapping is characterized by the following. If and only if pi is a push forward of the Lebesgue measure, by this inverse x mu and x nu. If and only if pi, the measure of this infinite rectangle, x, minus infinity a minus infinity b, is the minimum of the two accumulation function. So in particular, monotone maps are unique in the class mu nu. So therefore, any there is only one measure in this class which is monotone in this sense. And if mu is without atom, then it's actually a monotone map, because if mu has no atom, then f mu is continuous, and we can consider, instead of x, reparameterize it as f mu of x. And it's a continuous parameterization, then we get a monotone map. So if the cost function is h of x minus 1 by h in convex, then the optimal pi is monotone. That's the term says. So if mu is without atom, then the Mon solution is also monotone. And the Kantorovich distance between mu and nu is given in this way. How we see it? Because we can, you see that we can use this representation of pi to write the integral of hx. Let me write it here. So the definition of the Kantorovich distance in this case is h of x minus y, gamma dx dy. The gamma is the optimal mapping, and gamma is given, or let's call it pi now, not gamma. Confusing because usually I call pi mapping, but here I call pi a measure. So pi here is a measure given in this way. So if we use this definition of pi, then we can write it. We can replace this pi by the push forward of the bag measure with this function x mu x nu. So this will be equal to integral of h of f of x mu x. And that's precisely what is written here. Just put this. X. Okay. This is precisely what the push forward do. You take this function and put them in the variables. So we have this representation of the Wasserstein distance between two probability measure mu and nu, and this is the term says that this is optimal if h is convex. If h is strictly convex, then this is the only minimizer. Very special cases where h is just the distance, power 1. Then this is convex, but not strictly convex. So it's not unique in p equal 1. But nice observation is that in this case, we can write the distance, the integral not of x by my x mu minus x nu to the power 1, but also as f mu minus f nu. And the reason is that Frobenius theorem, if we look at x mu and x nu, or the integral of x nu minus x mu is just the area between these two curves, but we can calculate the area with respect to the variable here, we get the same area. And f is the inverse of x. So only in this case of h being the distance, we can represent it in this form, just by using the accumulation function. And it's not unique. The transport. So there is optimal transport corresponding to this is not unique because we can easily see that it doesn't matter. Any mapping which is monotone will give you the same distance. Now let me think the following calculation. I want to consider the distance between I want to fix the probability to measure mu and perturb it by small measures, epsilon g1 and epsilon g2. Suppose suppose mu and g are g1, g2 are smooth functions, have smooth densities. So let's make this calculation and see what we get. We want to push this measure to this measure in an optimal way with respect to WP. P is bigger than 1. So let GI be the accumulation function for of this small g. Right? And F is the accumulation function for mu. And then the accumulation function for mu plus epsilon g will be F mu plus epsilon gi. And if we invert it, and again under the smooth condition, we can write the inverse function and expand it in epsilon, and we get it the inverse function will be the inverse of mu, as the combination function mu, minus epsilon, the derivative of this function times gi. But remember that f is the derivative of the combination rho, the density of u is the derivative of the combination function, then here you have to put 1 over rho. That's a typo. It's 1 over rho. So if we change variable, we get that this WP is actually equal to epsilon to the power p times the integral of the derivative of the inverse accumulation to the power p times the p power of the difference of the accumulation function of g. Or we can write it, we can change variable to x and transform it to replace x to x prime to 1 over rho and dy to rho dx. So we end up with this integral over the line, rho to the 1 minus p times g1 minus g to the power p. So you see that if rho, the density rho is zeros in some interval, this will be infinite. Yeah? Why it's infinite? Because it's really much bigger than the p power of epsilon. The particle have to jump if the density mu has a gap, then particles have to jump on this gap. So they pay a price of order epsilon, and then we get something of order epsilon and not epsilon to the power p. But if we take this limit, as epsilon goes to 0, we get this integral, and I call it the conditional Wasserstein distance between G1 to G2. So this is actually this generalized to any dimension. Just prove it in got a explicit representation in dimension 1, but we can have a representation in any dimension. We may see it later, but in the meantime, let's see what happens if we take the maximum of this conditional Wasserstein distance over all probability measure. Yeah, what it is? Well, we just have to minimize this on all the CT rho, which has integral 1. So we use so we calculate it by using the Lagrange multiplier with the constraint integral of rho equal 1. You can easily solve for this, and we find out this is just the minimum happen if rho equal for a constant rho. So this is just the integral of the accumulation function. The difference between accumulation function, which is, as we saw, the Wasserstein 1 distance between G1 to G2, and this is the minimizer. Oh, it will be not 1, but it will be this weighted this distance between G1 to G2 normalized by the L1 norm. Just to make intuition here, you see what happened if I want to take particle or data function from x1 to x2 to move it a distance, say L. So the cost of moving a particle from x1 to x2, distance say 1, is just, and it's the mass of the particle is epsilon, it's just epsilon, right? Because it's epsilon times the distance to the power p, and the distance is 1. But what happens if we want to do it on the background of a uniform density, say? So we have a uniform density here and here, so we want to push this distribution to this distribution. So here we can do something much better. We can push. Maybe I have it on the next slide. No, we can push the first particle distance, which is epsilon distance. So suppose this is a uniform 1 distribution. So we push it distance epsilon. We pay epsilon to the power p, and the next, and then we push it another distance epsilon. So we make 1 over epsilon steps. Each one of them costs us epsilon to the power p. So we end up with a cost which is of order epsilon to the p, not epsilon. So this is really like something which makes the movement much easier. But if you have a background view, and this is reflected in this integral. If rho is it turns out to be uniform because I assumed here that G1 and G2 are 2 delta functions. So the difference between, so here, when I wrote the optimal rho, if G1 and G2 are accumulation function of 2 delta function, then this will be just a constant, right? A constant between x1 to x2 and 0 otherwise. So this will be the optimal the optimal mu, which had to communicate between x1 to x2. If this is not uniform, then it was more, but still of order epsilon. Right? If this is not uniform distribution between them, so we want to push this one to something which has a bump here. This will be bigger than the W1 distance between these two, which is, but still of order of the same order 1 in this case. Okay, so I think I will finish here because I have time and we more or less finish this subject of one-dimensional transport. Okay, thank you.